So earlier today, Brett gave a talk where she introduced this Tycho ray that wraps over the South Pole. In this talk, I'm going to be providing a radar characterization of the ray, and then more specifically over the Hayworth landing site, candidate landing site. Next slide, please. There we go. So the first radar characterization of a part of this ray was in Wells et al. 2010 in a paper in JGR using Artemis S-band radar observations of the moon. So in their paper, what they identified was that some of the small craters in Newton crater and Newton A crater had an asymmetric ejecta feature that was bright in CPR. And so in the image I'm showing you here, on the left side is a context image in the A and C. And then in B and D, it's that CPR map overlain onto those images. And this is from their paper. And so I think it stands out better in the Newton A crater. So in part D, you can see that some of the small craters that they have red circles around have this asymmetric ejecta that's elongated behind the crater. It kind of looks like this teardrop shape. And they were able to see that shape, that teardrop shape, lines up really nicely with where the Tycho ray was coming from. When they did a SFD study, size frequency distribution study of these small craters, they found that they can rule out that they're not part of the primary impactor population, but they did see that the SFD of these craters is much shallower, or just shallower than one would expect from secondaries. But looking at the general geology of these craters, the preservation state and whatnot, they were able to provide further evidence that these are likely secondaries from that Tycho ray. Next slide, please. And I won't go too much detail into this since Brett already gave a great introduction to Lola data, but um, using QuickMap, I just took overlaid the Lola reflectance data onto the moon globe here. And so I'm telling where Tycho is. And in the yellow arrows, I'm showing you where that ray is nicely extending all the way down to the South Pole. And on the left-hand side, you can see that it zoomed in to exactly the South Pole and highlighting where Shackleton crater is. And those yellow bars are showing you that they're nicely going into that Artemis candidate landing site region. And so we're going to try to characterize that ray in using mini RF radar. Next slide. All right, so let's start off with like a snapshot of the South Pole. So on the left-hand side, you see a controlled polar mosaic um, from mini RF S-band radar data, and I'm specifically showing you the opposite circular polarization. In this image, I've controlled both for the east and west looking data, and I've put them together. In the yellow boxes, you see the candidate landing sites, and then the magenta arrows, um, you see that I am highlighting the ray as it's coming through. So you see that it's nice and bright in OC. And although I'm not showing you the SC, same circular map, it's also bright in SC. Um, Now, if you're like me and stare at radar images for way too long, you could kind of squint and then not see this, and then squint again and see it again, and then start convincing yourself maybe it's not real. So I took a different view of this, and another way of looking at radar backscatter is by decomposing it into its primary components, and so that is volume scattering, the odd bounce scattering, and even bounce scattering. And so what we typically do here is that we call this an MCHI decomposition. And the intensity from each one of those different types of backscatter is then assigned to RGB space, and you put them together and you get this really pretty rainbow type of plot. In this time on the right-hand side, I zoomed in again over those Newton craters so you can better compare with the Odysseal S-band data. And we see that the ray is primarily green, and we could also see that the craters that were identified with those asymmetric ejecta patterns are also popping up really nicely in super green, right? And so that means that the backscatter from these regions is dominated by volume scattering. And so that's a telltale sign of ejecta or fresh ejecta deposits. And so that typically implies that there's fine grained material within the 1 meter radar sensing depth. And the caveat here is when a radar person says fine grained material, I've learned it's not the same when a geologist says it. So we're talking about tens of centimeters plus or minus around that range. We can only give you a range because different sizes have a different efficiency in its radar backscatter. But we can tell that this has a nice ejecta looking backscatter. Um, Next slide. Now, to do a further radar characterization, the first thing we always need to do is step back and always stare at radar and go, yes, you're complicated and you're mostly magic. The thing is that in radar, the radar backscatter that you see is produced by a bunch of different physical properties of the regolith. It could either be the topography, it could be the size frequency distribution of the regolith particles, it could be the morphology of the regolith particles, it could be the dielectric permittivity of those particles, so partially either its composition or its density, and so in these plots that you're seeing on the left-hand side, all of those different types of properties are plotted with different colors, and they come together to produce the overall modeled backscatter line in black. But the more important thing that you're seeing here is that radar backscatter is a strong function of incidence angle. And I'll highlight the modeled CPR, circular polarization ratio, is a nice function of incidence angle. And so when you're seeing something that is high in CPR, is that because it's rough, or is that because it's a higher incidence angle, or is that because of 5 million other things? The context really matters. And Caleb presented a great abstract and poster at LPSC where he demonstrated that the mini RF data clearly follows this nice expected trend with incidence angle for CPR. And so that's what you're seeing in the middle plot where the data, the actual mini RF data is all of the dots and the color are representing the number of data points that are there. And then the black line is his best fit line to that function. And so yesterday you saw plots that were normalized with respect to that function. Here you're going to be seeing plots that are normalized with respect to the green line. The green line is Caleb and I have been working to produce a radar scattering model that best replicates not only the function of CPR, how CPR varies with incidence angle, but also how OC and SC vary. And that scattering model, the two components that one can vary inside of it are the dielectric permittivity of the material and what we call the roughness parameter or the shape parameter, which typically most people say it's about topographic roughness, but really it's a bunch of different types of roughness put together. But the little knobs that we found that best fit everything match really well with the expected dielectric permittivity over regolith terrain and the typical roughness of it. And so with this type of model, we can then normalize, in a sense, the radar data and better pick out differences in roughness and dielectric permittivity. Next slide. So here's again that controlled polar mosaic, but now a little bit zoomed in. And the color is then showing you differences with respect to that model. So warm colors are higher backscatter than one would have expected, and cold colors are lower backscatter than that model would have expected. And you can see in the magenta arrows, I'm highlighting again that nice Tycho ray, and then I'm zooming in back into those Newton craters just to demonstrate that I can reproduce the LSUO results in terms of those nice asymmetric ejecta features. Next slide. But we're here to learn about the candidate landing sites. And so here's identification and characterization in one specific place, and that's Hayworth. So the magenta box is Hayworth plus the context region, and dotted box is the specific Hayworth region. And there you can see several craters that have that nice asymmetric ejecta that kind of looks like a teardrop shape right behind it. The backscatter is higher than expected by the typical scattering of the lunar surface. We see several craters that have that type of feature. And so with the mini RF data, in terms of exploration science, we could say, hey, go right here if you want to increase your chances of being able to sample Tycho disturbed material caused by those secondaries. But we could also go further than just saying go here. Next slide. We can also start characterizing the regolith material in that region. Um, so here's my little getting on the soapbox. Don't use CPR. Instead of using CPR, there are better ways of looking at identifying roughness or regolith properties. And one of those ways was suggested by Anverki and Sriram Biravasu. And in that, you look at each of the polarization components separately from each other. And what they found is that if you fit a line to those data, then the intercept is related to the dielectric permittivity of the material, and the slope of the line is then related to the actual wavelength scale scatterers. And so on this plot, I'm showing you an example of one of those asymmetric ejectiles found in the Hayworth candidate site. And then as context, I picked out a nearby crater that was high in radar backscatter, demonstrating that its ejecta is rather recently emplaced. And so that's Wapowski crater. And if we then fit the line and do the ratios, we can see that the asymmetric ejecta has a intercept that is lower than Wapowski. So that means its dielectric permittivity is likely lower. And so that means we're looking at a less dense material. And the slope is higher than Wapowski. So we're looking at wavelength scale scatterers that are either less or have a smoother morphology. But given the type of intensity of backscatter that we're seeing, the interpretation of this region is that the asymmetric ejecta is likely less dense and composed of less blocky material. So don't expect to pick up like a huge block there. You're looking at smaller stuff. Next slide. And in the end, the Brett had already reviewed why it would be important to sample these type of regions, so I won't go into that. But I'll just say mini-RF data is super awesome, radar is awesome, and it improves the ability to inform where you should sample, and also helps inform in terms of regolith properties. And with that, I'll just end it.